waiting for me to finish?
Greetings and welcome, friends. We're taking a look at 507 for the second time. Specifically, we were talking about Descartes' rule of sign, where we were able to determine the possible number of positive, negative, and imaginary roots. So taking a look at this is an x to the 14th. How many roots must there be?
14.
Right, there's going to be a total of 14. And using Descartes, I'm going to count the sign changes. That's no sign change. That's one sign change. That's two sign changes. That's three sign changes of g of x. Meaning, I'm going to skip a couple lines here as well here, just so you know. That means I have, for positive, negative, imaginary, we have three. Positive is our first possible combination there. Let's calculate what g of negative x is, because that's what I have to do in order to determine the other thing here. And really all that's going to matter is whether or not these are even or odd exponents and whatnot. Negative x to the 9th. And plus a negative x minus 1. So this is going to equal, that's positive x to the 14th plus positive x to the 10th. Negative x to the 9th becomes negative, but multiplied by a negative becomes positive x to the 9th. Plus a negative x becomes minus x, and then minus 1. So it looks like when I count those sign changes, none, none, 1, and done. Bow, 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 bow. So that means I've got 3, 1, and what's the possible? 10. That's right. Has to add up to this 14 we mentioned earlier. It looks like there's one more combination, and that's when you reduce these by an even number. So subtracting 2 from 3, I'd get 1, 1, and 12. And the reason these reduce by an even number is because the imaginary ones were increasing by an even number, right, when those were decreasing. Well, the reason that imaginary have to increase by an even number is because they always come in pairs, right? If you had an imaginary friend, you've got an imaginary enemy. So I can never just have an odd number of imaginaries. So Hank, that's actually all you had to do for this problem. You didn't have to find all 14 of those zeros, which is good. We just have to find out what kinds there were, and that's it on that. Problem 33. It says, given a function of one of its zeros, find all of the zeros of the function. So I know that 3 plus 2i is one of my zeros. Hey, wait a minute. If 3 plus 2i is a 0, what does that mean? I also know. 3 minus 2i is also a 0 because them there imaginary zeros come in pairs. So that means a depressed polynomial that I'll call g of x is going to be containing factors that have those zeros. So x minus a 3 plus 2i times x minus a 3 minus 2i. Make sure we're writing down corrections if we haven't gotten this correct. And I can simplify that. That's x minus 3 minus 2i. Whoop, whoop. And x minus 3 plus 2i. Right. So now when I triple distribute this out, I'm going to multiply the x by all of those. I'll get x squared minus 3x plus 2x. Oh, classic right there. Negative 3 times all of those would be negative 3x plus 9 minus 6i. And negative 2i times all of those would be negative 2x plus 6i. Yep. And negative 2i times positive 2i is going to be minus 4i squared. So let's cancel out what we can. Looks like 2x and 6i and 6i can cancel out. As far as friends, I'm going to have negative 3x and negative 3x. And positive 9 can combine with this, which is really going to be plus 4 after I change that I squared to a negative 1. This problem's feeling really familiar to me. familiar. So there's a g of x. Now, that actually doesn't help me find any other roots. That only contains the roots that I already knew about. But if I want to look for the other roots, of which I'm expecting how many roots total? 4. I know 2 of them. This one contains 2 of them. It means there's 2 other roots I'm looking for, and I don't know what they are. Oh, thank you. That's plus 13. Oh, good call. 9 and 4. Yep. There we go. Good call. Saving the day. Saving the day. So let's, in order to find my other depressed polynomial that contains the other 2 roots, I'm going to have to long divide by this guy.
I don't get long division.
Oh, then you should specifically go and practice some of it.
Maybe Khan Academy, that could be a nice little petite side quest.
Or sometimes we got to make our own side quests in life, you know what I'm saying? That's pretty deep. Pretty deep.
That's true, Mr. Wondy.
Let's see. Divide leading term by leading term. X to the 4th divided by x squared is, that sounds like an x squared. So I'm going to throw it in the x squared's column. Multiply x squared times x squared is x to the 4th. X squared times negative 6x is negative 6x cubed. X squared times 13 is positive 13x squared. Divvy it up. Divide. Nope, subtract. I lied. Bam. Subtract that. That's 0, 0, and 12 minus 13 is going to be negative x squared. And question?
Does the lesson today include long division?
Not directly, no. I don't believe so. No, I would say probably not. Although it can be used, I suppose. Bring down the 6x, and I believe this is going to be a double brought down sort of thing, but that's fine. We don't, even if we didn't realize it yet, we wouldn't have to. Divide leading term by leading term. Negative x squared divided by a positive x squared. That's a negative 1. I'll write that in the constants column right there. So I believe x squared minus 1 is going to be my other depressed polynomial. But to verify, let's finish this problem. Make sure its remainder is what? 0. Z to the hero.
The hero.
Oh. Negative x squared, positive 6x. Minus 13, subtract, and then you realize, oh, I did have to bring down that negative 13 there. And bam, 0, saving the day. El otro depresto polynomial, h of x, I'll call it this time, would have been x squared minus 1. Question, how many zeros does x squared minus 1 have? 2. And it turns out I can actually find them rather easily. X squared minus 1, set it equal to 0. I could solve that real quick. But bam, I don't even have to factor that, although you could. It's actually super factorable. It's a pattern right there.
And what are we finding here?
The other zeros. root plus or minus, and x is going to equal positive 1, negative 1. Right, bam. Oh, that's not a good box. The 1 became part of the box. So that means my zeros or roots for the original problem, if I wanted to list all of them, what were the originals? 3 plus 2i, yeah. Would have been 3 plus, well, I guess I could say plus or minus 2i, and plus or minus 1. So that means I had 2 imaginary and 1 positive, 1 negative. Actually, just for funsies, optional, unnecessary, you don't have to do this. Let's use some old Descartes on this. Descartes. And verify that I would have had 2 imaginary, 1 positive, and 1 negative, right? Let's check out what old Descartes would have told us here. I might as well point this out to us just so you can see the results. So let's see, for the positive, 1, 2, 3, okie dokie, okie. Positive, negative, I imaginary. So I would have had, I would have had 3 for the positive, possibly 3. Then I'd have to calculate the old r of negative x in this case. And Let's see if I can skip some steps. Well, let's see. This one's raised to an even, so it's going to be positive x to the fourth. This one's raised to an odd, so it would be negative x cubed times a negative 6x would have been positive 6x cubed. Even, that would have been positive. That would have become negative 6x, and that would have been negative 13. And if I count them, their sign changes. 1, none, none, 1, and done. So I would have had 3, 1, 0, or what's the other possibility? 1, 1, 2. Which situation did we actually have? We had the 1, 1, 2, right? Because I had 2 imaginary, 1 positive, 1 negative right there. Not too shabby. Not too shabby at all. So thanks for watching, Internet friends. Tienen un día el más bien del mundo.
I like the